start her presentation. Eu vou falar inicialmente em português sobre ela e depois vou começar a falar um pouco sobre ela em inglês, beleza? Então, a professora Alessandra, ela se formou como graduação PhD em Física pela Universidade de Pisa. Então, ela trabalhou também em muitos institutos de pesquisa como pós-doutorado e um pesquisador de alto nível. Ela é professora na Universidade de Pisa since 2005. As linhas de pesquisa que ela tem interesse, ela trabalha bastante com nanopartículas, cristais e nanocristais. E também tem interesse da preparação e caracterização, espectroscopia óptica dos materiais voltado para aplicação na fotônica. Aí, ela also participou em um projeto internacional que chama Virgo, que é sobre ondas gravitacional, mas parece que não, esse projeto já acabou. Ela tem mais de 160 publicações em revistas internacionais, baseado nos dados base de dados de Scopus. Ela tem um índice de H igual a 48. Então, tudo isso mostra que ela é um pesquisador muito ativo na área, e a gente pode aprender muito pela apresentação dela hoje. Beleza, antes que ela começar, eu vou falar também algumas informações, vou apresentar ela em inglês. Prof.ª Alessandra Toncelli has a graduate and PhD in physics from University of Pisa. She's also have participated in many projects during his postdocs, and she was a full researcher in Italy and other countries. Since 2005, she's a professor at the Department of Physics of University of Pisa. Her scientific interest initially was the growth and spectroscopy of crystalline materials for photonic application in visible and near infrared region. But she also has other works on the nanocrystals and nanoparticles doped with rare earth ions. Also, she has participated in a Virgo project that was about gravitational waves. And by all of this scientific career of her, she has more than 160 papers in the international journals, and based on the Scopus, she has a H index of about 48. All this information and shows that she is a very active researcher in the area, and it's a big pleasure for us to have her in our workshop. Professor Alessandra, you can start now, please.
Okay, thank you very much for this nice introduction, and most of all, thank you very much for having invited me to this international conference. It's really a pleasure for me to be here virtually. I'm virtually in Brazil. Thank you. My name, as you have said, my name is Alessandra Toncelli, and I work at the University of Pisa, where I started as a student. Today I will tell you about my latest results in the field of mid-infrared spectroscopy of trivalent rare earth ions in crystals, which I think is a very interesting topic. I hope you can see my screen. Is it okay? Can you all see? Okay, thank you very much.
Yes, that's fine.
Okay, so sorry, I started with a laser pointer, but now the mouse does not work, so I have to go back to the mouse pointer. I hope you can see it. It's not as nice as a laser pointer, but otherwise I have to switch from one to the other. So I think I will keep the mouse pointer. Okay. So why mid-infrared? Mid-infrared is a very, very interesting region, sandwiched between the near-infrared and far-infrared. It's usually considered the region in between 3 and 10 microns, and is very, very interesting because many molecules have rotovibrational levels here. So it's also called the fingerprint region because it's you can use it to identify the molecules and components of your sample, for example. So you can make molecular structure studies, or you can also study the collective motions, for example, optical phonons in crystals. And this is also the region where plasmonics has seen a lot of great advances in the last decades. There are many applications possible. Spectroscopy, of course, of materials is the first, but this has many applications for the environment, but there are also many medical applications or sensing applications in general. So there's a great motivation to work in this region and to develop powerful sources to make spectroscopy more and more sensitive in this region. At lower energies, you can find the far infrared region, which is also very, very interesting. It's in the wave number range from 100 to 1000 inverse centimeters. And below these, you can find the terahertz range, which is in between 10 and 100 inverse centimeters energy. And it's at the border with the electronics. But spectroscopy in these regions can be very, very useful for also for studying and characterizing materials, especially phonons. So that's why I will tell you something about this also. If you want to work in the mid-infrared, you have to use a special spectrometer, mainly Michelson interferometers, which are also called FTIR spectrometers, because after you acquire a spectrum, well, an interferogram, you have to perform Fourier transform to obtain your spectrum. This is why the name Fourier transform infrared spectrometers. Since there are many molecules that can absorb in this region, spectrometers are usually vacuum tight or purged with controlled atmosphere. Detectors are special detectors developed for this region. Some work at room temperature, like the TGS, but the best ones need to be cooled down because the energy of the photon is quite low and it competes with the thermal energy. So it's always better to cool down detectors and materials in general. There are also problems in finding the right materials for optical components because not many materials are transparent in this range. So it's not an easy region where to work with. You have to really use special techniques. And even more special is the terahertz range, where not many tools were available since a few decades ago. But now we have this nice spectrometer, which works in time domain. This is a completely different concept with regards to Michelson interferometers. The heart of this spectrometer is an ultrafast laser that is sent to an antenna. Usually this laser is an erbium fiber laser. And this is sent to an antenna where it generates carriers and holes which have a lifetime of the order of a picosecond. So what you obtain is a transient current in a time scale of a picosecond. So if you perform the Fourier transformation, you can see that a picosecond time duration current gives you a terahertz radiation. This beam can be treated as an optical beam, and it goes to the detector where you have a gated revelation that can give you the time variation of the signal. This is something unique in the optical region, because interferometers like the previous one well, all interferometers in the optical regions cannot follow the oscillations of the radiation field because it's too fast. But in this region, since it's in the terahertz range, modern electronics can follow this very, very fast oscillation. So what you get is not just the intensity of your beam, but you obtain both intensity and phase of your radiation and of your transmitted signal, for example, from your sample. So in one shot, with one single measurement, you can obtain both the absorption spectrum of your material and the refractive index. And this is really a unique opportunity in the optical region. As I said, it's the only region where this is possible. But if you want to make spectroscopy, of course, you need radiation sources. Yes, okay, you can use lamps, but lasers are always better, as you know. But there are not many laser sources in the mid-infrared region. The main ones are based on semiconductors, mainly antimonide 3.5 or quantum cascade lasers. These are very nice devices. They are very compact in size, and they are electrically pumped. So they are very, very practical. But they have strong limitations because, for example, they need to be cooled down to cryogenic temperature. The beam quality is not very nice, especially if you want high output power. And in any case, they are very limited as for maximum output power you can obtain. And also the tunability is not very broad. Another possibility is to use transition metal ions like cobalt or iron, for example, and they can be inserted as dopants into insulating crystals. In this case, you can obtain lasers that can be very, very powerful. There are not strong limitations in the output power. The tunability is quite broad, and the beam quality is also very, very, very good. But the main limitation is that the lifetime of the levels involved is quite short, so they can only sustain pulsed emission and not continuous wave. Other approaches have been developed in the last decades, and they are mainly based on nonlinear effects like parametric frequency conversion. That's what happens with optical parametric oscillators, or OPO for short, or different frequency generation, or DFG, or supercontinuum generation. These have very nice advantages because they can work at room temperature, and they have very large tunability, in some cases a very huge tunability, I would say. But the main limitation is that they have a complex design that usually must be realigned from time to time, and they also sustain only pulsed emission because since they are based on linear processes, they need very, very high intensity of the radiation that can be obtained only with ultra-short pulses. So the perfect light source is still missing in this region. That's why it's worth trying with different approaches. So why not trying with rare earths in crystals? This plot shows the whole list of rare earths you can insert in crystals. These are very, very well known for their emissions in visible and near infrared. Many very good lasers have been developed in these regions, and they compete with all other lasers, especially for the peak powers and also for the average power they can sustain, and the very, very good beam quality. Emissions from these levels can be either pulsed but also CW, because lifetimes of rare earths are usually quite long, and this is the main their main features, I would say. But there are not many information about the mid-infrared emission properties of these ions, despite the fact that there are many transitions between these levels that can emit in this region. For example, I can list you some of them in the 2 to 3 micron range, which is at the border with the mid-infrared region, from thulium, erbium, dysprosium, and neodymium, for example. But there are others in the 3 to 4 micron range, from holmium, europium, samarium, and praseodymium. Others are in the 4 to 5 micron range, from praseodymium, europium, terbium, dysprosium, holmium, and erbium, and thulium. And some are even beyond 5 microns. For example, in neodymium and praseodymium, which are the ions I will focus in the rest of my presentation. So these are very, very interesting ions for mid-infrared emission, because as you can see, there are many different transitions that can emit in this region. So why not? Why haven't they been already exploited for these emissions? I have to tell you that there are many problems because laser action is difficult, because the energy of the photon is low, so it competes with non-radiative energy loss transitions, and these are mainly due to the interaction with the phonons of the crystal. So you need a crystal with very low phonon energy, and that's the main problem you have to face. Moreover, even if you do not obtain laser emission, laser spectroscopy, mid-infrared spectroscopy of these ions is still very, very interesting, because many of the visible and near-infrared transitions that are used for lasers have the bottom laser level in one of the first excited levels of these ions, which are rarely being observed directly. So performing spectroscopy to the mid-infrared levels of these ions also gives you important information for the modeling and the understanding of the physics of near-infrared and visible lasers based on rare earth ions. So I hope I convinced you that it's worth working with these materials in the mid-infrared. Let me tell you something more about the non-radiative processes that can happen. Of course, the non-radiative transitions follow the energy gap law, which predicts that the rate decays in an exponential manner with a constant that depends on the host crystal. So low phonon energy is crucial for obtaining mid-infrared emission, but there are not many possibilities to observe the phonon energy directly. We usually rely on indirect measurements by observing the lifetime variation with temperature, for example, or other parameters. But with the spectrometers I showed you before, it's possible to perform a direct measurement of the phonon energy of crystals. I will show you an example later. This is a table that shows you the phonon energies of the main crystals that are used for near-infrared lasers. In the upper part of the table, you can find oxide crystals, which have phonon energies in the 500 to 1000 inverse centimeter range, and this is quite high for mid-infrared. In the middle, you can see a lot of fluoride crystals with phonon energies around 300 to 500 inverse centimeters. And in the bottom part, you can find chlorides, bromides, and even iodides. They are not here, but these have very, very low phonon energies, even lower than 200 inverse centimeters. So these are the best materials, but of course, when the phonon energy decreases, also the chemical stability of the material decreases. So most of them are hygroscopic. And moreover, they are very difficult to grow, especially they are difficult to be grown in good quality, because for laser application, you need really good optical quality materials. So very few growth facilities in the world can grow these types of crystals in good properties, with good optical properties. This is a work I have performed, not really for developing a laser in mid-infrared, but for filling the gap of missing information about mid-infrared levels. For example, I will show you the example of neodymium YAG, which is a very well-known crystal. It's an oxide crystal with high phonon energy. Unfortunately, it's not suitable for mid-infrared emission, but I could observe some interesting properties. Neodymium YAG is usually pumped with an 808 diode laser, but the emission of diode lasers do not really fit the absorption properties of neodymium quite well. So one possible approach is to co-dope neodymium YAG crystals with cerium, because cerium has these 5D levels up here, which show a very broad and strong absorption feature in the blue region. And this overlaps perfectly with the emission lines of blue diodes that are commercially available now. So one approach that have been used is to use cerium as a sensitizer. It absorbs the energy, then this is transferred to neodymium, and through non-radiative energy transfers, the upper laser level is populated, and you obtain one nice 1 micron emission from this transition. But cerium has also one 4F level, which is located in the mid-infrared. And as far as I know, has never been observed directly in YAG. And this level can interact with the bottom laser level of neodymium. So it's worth investigating the energy level position of cerium in this crystal, because it can be interesting for modeling the near infrared emission of neodymium. So this is an enlargement of the energy level scheme of neodymium up to the near infrared. This is the 808 pump laser. In this case, you have one non-radiative transfer to the upper laser level. And from the 4F3/2 level, you can have 4 different emissions at 900 nanometers to the ground state, 106, which is the most famous one, to the first excited level, and then 1.3 to the second excited level, and then 900 to the third excited level. This is what happens in near infrared, but neodymium has also potentialities in mid infrared. For example, if you pump to the 4I15/2 level, there's an intriguing possibility of cascaded emission, because these three transitions have similar energies. So it is possible to find a coincidence of frequencies so that you can obtain a cascaded emission as a ladder, like what happens in quantum cascade lasers. And these are all in the 4 to 6 micron region. And nowadays, it's possible to pump this level with erbium fiber lasers, which are very powerful nowadays. So this is the absorption spectrum of neodymium. You can see the transparency limit to around 5 micron. And these are the room temperature absorption from the first 3 excited levels in mid-infrared. We also performed this absorption as a function of temperature to identify the energy level, the exact energy level position of the stark sublevels of neodymium, and compared with the literature, you can see that we refined a little bit some of the energy level positions that were already known. But there's one missing line for 3I13½ that it's completely missing, so it might be a wrong assumption. For cerium, as I said, is not known. The energy levels are not in the literature, so we performed absorption in mid-infrared with cerium YAG crystal as a function of temperature to identify the various lines. Most of these are very, very weak, but they show the typical behavior as a function of temperature of rare earth absorption lines, so we could identify them as real lines, and we could find the exact position of the cerium energy levels in this material in YAG. So let's go back to the energy level scheme. As you can see, this is the first excited level of cerium. Now it's not an unknown anymore, but we can substitute it with the energy level position we observe directly. And we can see that there can be there really can be an interaction between the bottom laser level of the 1 micron, but also of the 1.3 micron transition with cerium. And this can be good for laser action because it can help deplete the bottom laser level through another non-radiative channel for enhancing the efficiency of the neodymium laser. But let's see if it's possible to obtain mid-infrared emission from neodymium. This is the usual energy level scheme. Unfortunately, I didn't have a 1.5 micron laser at that time, so I used an 808 laser pump. So I could, of course, observe the usual transitions of neodymium at 900 nanometers, 1.06, 1.3, and 1.9 micron, but also a small signal even beyond 2 microns. But these are not special results. But let's see what happens in mid-infrared. Going to mid-infrared, I could observe a certain signal in between 4.6 and 5 micron, really at the border of the transparency region of the material. As I said, these can match these 3 transitions, so it's not easy based only on the energy position, on the wavelength of this radiation. It's not easy to identify which of these transition is this one. But if you compare this emission with the absorption spectrum I showed you before at room temperature, you can see that the shape and the exact position is absolutely the same as the absorption one, the absorption spectrum. So we could identify this emission as the one from the very first excited level to the ground state of neodymium, which is, I have to be frank, is not the best for a laser emission because the bottom laser level is the ground state, which is not very promising. But in any case, it's remarkable that we could observe a 5 micron emission from a crystal that has phonon energy higher than 800 inverse centimeters. So really, it was really unexpected. I promised I would have shown you some results about the far infrared and terahertz spectroscopy. Here on the left, you can see the two phonon absorption lines in the far infrared region. This number is not wrong, it's really 50 microns, which corresponds to about 200 inverse centimeters. And you can clearly see two phonon absorption lines. And at even lower energies. You can see on the right the refractive index dispersion, which is featureless because there are no optical phonons here. So let me tell you just a few things about praseodymium in lutetium oxide. This is a sexy oxide, which is again an oxide crystal, but with phonons that are relatively small. And praseodymium, as I showed, has many emission lines in mid-infrared. This is absorption of praseodymium in the mid-infrared with a transparency region that ends at 8 microns. These are the absorption lines from the first 4 or 5 excited levels, both at room and low temperature. And with these results, we could identify the energy levels position. But let's go to the emission. We could observe a near-infrared emission from this high 3P0 level, but also some emissions from 1G4 and 1D2 levels in the near-infrared again. In the mid-infrared, we could observe some lines in the 4 to 4.6 microns range. And again, this emission resembles the absorption lines in red. So this comes from the first excited states to the ground state transition. But what's really remarkable is that we could observe a 7 micron emission, which has been identified as the 3F3 to 3F2 transition. And this is very, very interesting because it is equal to about 3 phonon energies of the crystal. And I think it's again, it's very unexpected that we could obtain an emission at these long wavelengths in such a crystal. The slope fits of these emissions could help us to identify the various energy transfer processes that were needed, bilinear processes to populate the emitting levels. So it's not a cascaded emission, but it's due to bilinear processes because the slopes are all higher than 1, nearly 2 in some cases. So in conclusion, I've shown you some results about mid-infrared spectroscopy of neodymium and cerium in YAG. Even if this material is not the best for mid-infrared emission, but we could observe the energy level position and revised or observed for the first time these results in literature. We could study the energy transfer processes, and we could observe a 5 micron emission in neodymium YAG. For praseodymium, again, we observe the mid-infrared absorption at room and low temperature, so we could observe or revise already known results in literature. But the remarkable properties is that we could observe a 4.4 micron emission, which is less than 4 times the phonon energy of this crystal, and even 7 micron emission with less than 3 phonon energies in this crystal. So this work has been performed at the University of Pisa, but in collaboration with IKZ in Berlin and University of Hamburg, with the persons of Dr. Alexander Heuer and Professor Christian Krankel, that I have to really thank for providing me the sample to study. So that's all. Thank you for your attention, and thanks again for having invited me to this nice conference.
Okay, thank you very much, Professor Alessandra. We have some questions here that, about the presentation that I would like to ask Felipe from Zoom. He has asked that is synchrotron light an effective light source for mid-infrared spectroscopy?
Synchrotron light is absolutely perfect in any region from ionized radiation to the terras.
Professor Alessandra, I cannot hear you. I cannot hear you.
No? unmuted. Now can you hear me?
I can hear, but there's some problem that the voice is not clear.
I don't know why. I didn't change anything in my computer.
Can you restart the audio?
Okay, can you hear me now? No?
No, still it is not clear.
It's good that I could finish my presentation, but now I don't know what the problem will be. I can increase the volume. No, I think it's okay. I increase the volume of my microphone. Is it clear now?
Unfortunately, I can hear you, but it's not clear.
Is it a problem with the web transmission or with the microphone? Is that mute? Okay, let's try again.
Unfortunately, no.
Try to mute your microphone. Maybe my microphones have a problem together. As far as I can see, my microphone works well. Now, can you hear me now? Can you hear me now? Yes? Okay, great. Thank you. So I was saying, yes, absolutely. You can use synchrotron radiation. Synchrotron radiation is very good in any optical region. But the problem is that you cannot have synchrotron radiation in your lab. You have to ask for beam time at special facilities, and there are only few facilities around the world. We have just one in Italy, for example. So yes, of course, that's the best, but you have to have a special project, apply for beam time, and so on. So all these types of problems. So if you can work with tabletop sources, it's of course more practical.
Okay, there's another question that I found interesting. Francisco from Zoom, he's asking that, is it possible to use erbium ion as a synthesizer for neodymium in order to enhance the emission in mid-infrared?
Well, erbium ion has a lot of energy levels which can interact in between the erbium ion levels and also with neodymium. So yes, you could co-dope with erbium, but you will trigger a lot of energy transfer processes, especially bilinear processes, that I'm not sure you can really control, and some of them can be detrimental to the final goal you want to reach. So erbium is not maybe the best. It's better to use ions that have very few energy levels, so that the interaction is limited and you can control it a little bit better.
Okay, I have one personal question here. It's from me. that do you think that the techniques, that spectroscopy techniques that we are using now have a lot of limitations?
The ones I used, you mean?
Yes, for example, in your work.
Well, of course, yes. As I said, synchrotron radiation would be much brighter, for example. But these instruments are very practical to be used in a lab. Once you buy them, maybe they're not the best, the absolutely best, but once you have in your lab, you have them in your lab, they are, I would say, almost maintenance free. So apart from, for example, changing a lamp once every 10 years, I don't know, you don't have many problems in using them, even if the signal to noise ratio is not the absolute best. Maybe if you build a special, you design your own experiment with special equipment, you can do better, but that's a great effort, of course.
Okay, thank you very much, Professor. It was a pleasure for us to hear you and about your